My name is Dayan, an assistant professor from the University of Alabama at Birmingham. I'm presenting our work titled BERT, a pipeline for stock price prediction using news. Here's an overview of this presentation. Let's first take a look at the problem motivations. It is well known that news provides important buy and sell signals in stock trading. Consider, for example, the stock of Zoom shown on the slide. On April the 2nd, Zoom CEO apologized for security issues, following which Zoom's stock price falls for a couple of days. Also, on November the 9th, the good news on the effectiveness of COVID-19 vaccine causes Zoom's stock price to fall. But overall, since the pandemic generates a lot of Zoom users, Zoom's stock price has risen a lot this year. As another example, consider the stock price of Uber. On April 28, Uber discussed a plan to lay off employees, following which there is a significant drop in the stock price. Twitter has made messages on stocks freely available. For example, if we search for the stock symbol of Apple, we will find a lot of tweets discussing the stock. However, we find that most tweets are actually not relevant. For example, this tweet is discussing Bitcoin price at different market caps, while this tweet is on how a 10-year-old kid defines Apple and the others. This tweet is more about Apple's CEO Tim Cook than Apple itself. This tweet is on the holding of an investor, but it is unclear whether following this investment strategy will make money. So in summary, the challenge in getting useful news signals from Twitter is that the tweets can be very noisy. Another issue that may introduce irrelevant tweets is the word ambiguity. For example, this tweet is regarding American singer-songwriter Fiona Apple, not about the Apple company. For those news that are relevant, we then need to decide whether they favor or hurt a stock. For example, the first tweet here indicates that coronavirus could hurt iPhone sales, and thus it hints a drop in Apple's stock price. The second tweet is more interesting. It indicates that Tesla and Microsoft are doing well, but Facebook is not. So we can see here that the context of the word matters on whether the attitude toward the stock is positive or not. Our solution is based on two breakthroughs in deep learning. The first one is sequence models, such as the various recurrent neural network structures, which take a sequence of data as input and emit a prediction in the next step. We use a sequence model to extract features from the historical price data. The second one is the various transformer models for natural language processing, such as BERT, which allows us to fine-tune a pre-trained NLP model for various NLP tasks. We use Google's BERT to extract features from news data. The model we propose is called BERT, which takes the name from both BERT and LSTM, or long short-term memory, which is a kind of recurrent network unit. We next overview our approach. Our news-based predictive model contains 4 components. The first component is a Twitter crawler, which obtains those tweets that mention stock company names. The second component is a filter, which removes those tweets that are not relevant to the stock companies themselves. The third component is a feature extractor that extracts a vector of price predictive features from each relevant tweet. Finally, we have a recurrent neural network that takes historical prices and news features to predict the price in the next time step. The first three components are illustrated on this slide. When an irrelevant tweet arrives at the relevance filter, the filter will remove it. In contrast, a relevant tweet will pass the filter and will be forwarded to the feature extractor to extract features that are indicative of whether the price of a stock will rise or fall. The last component uses a sequence model to predict the stock price in the next step. The input to the model is a sequence of historical prices. However, in some of the time steps, there could be relevant news. We can extract features from those news, and these features are then concatenated with the prices to serve as the model input for price prediction. We will then get our prediction in the next time step from the model. Next, we briefly introduce how our data are collected and annotated for training. Since both components are tweet classifiers built with Google's BERT, let's first briefly review BERT. BERT takes one sentence, or a pair of sentences, as the input. The sequence of words are transformed by transformer encoders into their embeddings that capture the word context using the self-attention mechanism. After multiple layers of encoders, we get a pooled output that encodes the features from the entire sentence. The head associated with the pooled output is actually connected to the NSP task during BERT pre-training, which predicts if the second sentence in the input is the one that naturally follows the first sentence. In summary, we get the sentence features from the pooled output. BERT also outputs a sequence of context-aware word embeddings, one for each word in the input sentence. Those embeddings are learned using the task of masked language modeling. Specifically, in BERT pre-training, a word is masked, and the task is to predict this word from other unmasked words in the same sentence. In summary, the embedding of each word in the sequence output is context-aware. In our model training, we mask each word that represents the stock being considered. Since the stock name usually does not impact the price direction, but rather the context does. We also do some data cleansing to remove URLs and other special symbols in the tweets. Let us consider a tweet crawled using Microsoft as a search term. We want to extract features from the tweet, and meanwhile extract context-aware feature embeddings of the word Microsoft in the tweet. For this purpose, we'll compute a bitmap for the tweet, where if a word is Microsoft, the corresponding bit is 1. Otherwise, the bit is 0. The tweet is then input to the BERT model first. And we will get the pooled output for the entire tweet, as well as a sequence of word embeddings. We then use the word bitmap to mask the sequence output, so that only those embeddings that correspond to the word Microsoft are aggregated by summing the embedding vectors. This summation is the context-aware features of Microsoft. We then transform both the tweet features and the Microsoft subject features by dense layers, and concatenate the two, transform the feature vectors into one large feature vector. This feature vector will be used by prediction tasks. We remark that since BERT is pre-trained, our fine-tuning is actually training the weight parameters of these two dense layers. For training purpose, we will connect the concatenated feature vector to a classification head that uses cross-entropy loss. For the relevance filter, we have two classes, while for the tweet feature extractor, we have three classes indicating whether the stock price will rise, remain the same, or drop, as shown on this slide. In this way, we ensure that the extracted feature vector is indicative of the price direction. Now that we are able to extract features from each tweet, we next see how to use these news features together with historical price sequence to predict the price in the next time step. We use RNN to take the sequence of historical price and the news features as the input to predict the price at the next time step. We adopt a autoregressive design, and for the RNN unit, we choose to use LSTM. This model has been found to work the best in our prior work when we expand the prices with technical indicators. And here, we are replacing the technical indicators with extracted news features. Specifically, we discretize a price sequence into time steps. In our study, we use 1 day as a time step, since this allows enough news to appear in a time step. In each time step, we compute a median share price for the stock, which basically weights the prices with the volume of the stocks traded. These prices are only half of the input. We also have some news popping up from Twitter in some of those days. We'll extract features from these news using the feature extractor that we described before. And if there are more than one piece of news about the stock in 1 day, we compute the average of those news feature vectors in that day. These feature vectors constitute the second half of the model input. For those days with no news, we use the zero padding. Finally, our model outputs the price prediction for the next time step. To train our model, we use an autoregressive design. Specifically, we let the LSTM unit at each time step emit a price prediction for the next time step, and compare it with the ground truth to backpropagate the errors. Our price regression model is trained with a mean squared error. Note that since the LSTM units share the same weight parameters, our backpropagation from every time step will train this parameter better than if we only consider the prediction at the last time step. Finally, we briefly overview the results we obtain. We compare our regression-based method with a naive method that trains a price direction classifier. Note that our regression model can also be used to predict price direction, since if the predicted price is higher than the previous time step, then the direction is up. In this slide, we show the ROC curve obtained for the price direction prediction. So there are 5 methods that we consider. Okay, the first 2 are classification methods, where cent means that we use both price and also the news features, while price means we only use the price alone for classification. And our actual method, these 2 classification methods are baselines. Our method is using regression. Okay, it's a counterpart in regression. And for the state of the art, we are comparing with the StockNet shown here. We can see that the regression models that we are using are consistently better than the classification models in this ROC curve. For classification, we can change the positive class probability threshold to get an entire ROC curve. But for regression, we only have 1 point, with fixed positive rate and a true positive rate. As for price regression, RegCent is the algorithm that expands price with news features, and we can see that it consistently outperforms the algorithm that only uses price alone. The error is much smaller. Here is a visualization of the price of Apple. The red curve is our prediction using both price and news features. And we can see that it is closer to the blue ground truth curve compared with the yellow curve, which is predicted by using price alone. This ends our presentation, and thanks for your attention. Now I will take your questions. You can also contact the first author, Yinzhe Dong, with questions.